Good afternoon, everybody. My name's Charlie Nicklin. I'm the Chief Executive of IAgrE, and I'd like to thank you all for joining our Christmas presentation. Where's that year gone? I can't believe it's Christmas already. I'd like to welcome IAgrE member Ray King for our lecture today. Ray is a graduate at Harper Adams and has worked in a number of the more traditional machinery manufacturers in our industry. And then in mid-2019, Ray joined the small robot company and is now their lead mechanical engineer. Ray is going to take us through the team's journey as they've developed robotics and artificial intelligence to help farmers reduce both costs and the environmental impact agriculture can have. So just before Ray starts, as normal, you're all currently muted. So if you want to ask a question, please use the chat at the bottom of the screen. And then at the end of the presentation, we'll unmute you so you can ask in person. Okay, over to you, Ray.
Hi, yeah, my name's Ray. I'm the lead mechanical engineer at a small robot company, and I'm going to give you a bit of a quick run through of kind of our development process and some of the learnings that we've had from developing our technology over the last 3-4 years that I've been at a small robot company, and kind of where that's led us to. So what are we all about? What is small robot company all about? So our vision is that per plant farming will be the dominant farming system in the next 20 years. Any farm growing any crop anywhere in the world will be able to gather intelligence on each individual plant and take action on each individual plant. So that's the vision, and then I want to sort of take you into some of the details. So what's the concept? So the concept is 3 robots, and if you've been following kind of what we're all about, you might know of this, but they're Tom, Dick, and Harry. Tom is a scanning and scouting robot. Dick is a weeding robot. Harry is a planting robot, and then we've also got Wilma, which is the user interface, planning, and AI software. So Wilma's the brains of the outfit, and the robots are kind of the doers in the kind of ecosystem that we've got of robots and software. I've got a couple of videos here to run through. So this shows you kind of a concept, some sort of concept art effectively of our scanning service, and then how we can repurpose some of those components into various different formats to do the weeding aspects of the job, and then moving on to the planting aspects. So I'll dive into a little bit more detail in this, but it's kind of, we've been looking at a kind of a modular approach, and that's something that we've been developing specifically this year. So yeah, I'll talk about that in a bit more detail later on. The next video is just a very quick run through of kind of the user interface of the Wilma software. So shows you zooming into a field, and then basically accessing the data that the Tom robot has gathered, and also not just the data, but more importantly, the insights that the Tom robot has gathered. So looking at the per plant information that we've been able to capture with the cameras mounted on the Tom robot. So if I go to the next slide. So what does Tom do? So I've touched on that a little bit. So we've got the raw images. That information is stored on the robot. It's removed from the robot at the end of the day after a day out in the field. It's then uploaded onto Wilma, and then we get our per plant view, which is basically all that raw imagery run through a piece of AI, which basically identifies what's crop, what's weeds, what different types of weeds we've got there, green area index, all sorts of different insights that we can access once we've got that imagery. So kind of what does Tom do? And this is a little bit more detail about the information that Tom robot's gathered. So in the top left, you've got actual imagery from the Tom robot. In the bottom left, you've got the information as analysed by the Wilma AI, so it's identifying where it's found various weeds. I'm not sure exactly what those weeds are, but yeah, it's basically identified weeds in the field, and also identified the crop and where the crop is. This information can then be pulled through into a weed map, and we now have the capability that we can take that weed map and turn that into a spray map. So looking at this particular example, we can save 51% of chemicals with a 1 meter by 1 meter treatment area, with a spray, basically with a nozzle controlled sprayer. We can take this map, load it onto the spray, and then we know the areas that we need to go and spray. So we're now in a really good position where we've got the robot gathering the high quality data, but we were also able to actually action some of our insights, and this has been one of our key developments this year. I'll move on. So what I want to talk about in detail today is the Tom robot and the Tom sort of platform. When I started a small robot company, Tom was what you see on the bottom left there, a small sort of remote control vehicle with a GPS unit attached to it, and it was a really good little exploratory tool, and it got the team out into the fields and sort of understanding conditions a little bit more, and what we needed to improve. It was also relatively cheap to sort of build, test, trial, build, break, repeat. Get it out in the field and get data and information. Tom version 1 was what was the next development, and the idea behind that was trying to make something that was able to gather data at a more commercially viable scale. And then, as you can see there, we've got Tom version 3. Tom version 3 is what I'm going to be focusing on in this. So a really short video here of Tom version 1 trundling around. Basically, quite a heavy robot, very slow, heavy batteries, coverage rate was incredibly low, and we had lots and lots to learn from this robot. It was a stepping stone to sort of getting us to where we are today, and I hope, as you'll see, was sort of the progress we've made since this, and the learnings from this have been absolutely vital. So Tom version 1 was what I arrived at Small Robot Company, along with a few other sort of key people to basically help to bring this robot to life. So as I said, let's just move that. There we go. So this is the development process that we followed for Tom version 3. So we had the initial requirements and the learnings from Super Tom version 1. So we basically sat down as a team, discussed what went well with version 1, what went badly. We also looked at if there'd been any changes to the initial requirements that we'd set out for the robot. Had there been any change in sort of coverage, the amount of coverage a robot needs to do in a day, or whether there was any other sort of limitations that we had. Pulled all that information together, and then we basically created models and simulations which pulled in information from testing from the initial robot, and also stated any assumptions around the models that we pulled together. And then we coupled this with validation testing. So we basically said, we're going to run some models, run some simulations, we're then going to do some testing against those models, and then we're going to use that testing to validate our assumptions, validate our models, until we're at a point where we've got enough confidence. We could never be fully confident, but enough confidence to allow us to move forwards with the design. And then that allowed us to then pull out subsystem and component requirements and specifications, and then beyond that, component and subsystem design. So we were quite a small team, and we're a startup company, so this was all very fast paced. But what I tried to do is pull out the approach that we used, and try and sort of pull that into something visual that can be shown and talked about. So if I go to the next slide. So this was our sort of learnings from the Tom V1 performance. So we had a numerous list of things that we didn't like about the robot. We had problems with drive torque. It was very heavy. We had a lot of ground pressure issues and sinking in wet conditions, problems with water resistance, poor stability, poor chassis stability. a really long list, but actually an incredibly valuable list that helped us to move forward. So once we kind of conducted the appraisal of the version 1, once we built that robot and put it to the test, we then took that information and basically started to build our models. So we created a model around drive torque calculations and some testing. So basically created a spreadsheet, and we're basically using some sort of understood and known models for traction, and then we took that information and then we applied it through to actually some testing. So we said, right, okay, we'll take those assumptions, create that model, test the version 1, and do the results we get from version 1 match where we are now? And we honed in our models until we were at a point where we were able to, as closely as possible, kind of match the results we found, and then that allowed us then to move forwards based on assumptions that we had for the next version of the robot, which were around the sort of size, the mass of the vehicle, and various other characteristics that we kind of had in play. And that's where I was saying it's very key to state assumptions in the models, so that when we come back and revisit them, we know we might not always get things 100% right, but if we know what we assumed, we can then always come back to that information and make adjustments, and we kind of know the risks that we're taking as well in actually developing the technology. So another key piece of testing we did was steering torque testing. So we specified the design of our own steering actuators, as we call them, and we worked with a consultancy that helped us to do that. But before we could get going, we had to really understand how much torque it was going to take to actually turn our proposed tires and turn our proposed wheel options in the field through a number of assumptions. We tested them on tarmac. We also tested them on basically a grass lawn, taking the worst case from those, and then using that information to sort of basically push us in the right direction when it came to peak torque requirements for our steering actuators, to make sure that we didn't design a unit for our robots that was a million miles away from what we needed. So that's another very useful. Contact patch and tire deflection testing. So again, alongside this, we used the same rig that we used for steering to determine our contact patch. So basically put a known load again on top of the wheel, measure the deflection, also measure the also then we used a tray with some soil in it, basically to just show an imprint of where the tire was and what our contact patch was, so that we had a much better understanding of our of the ground pressure that we were putting down. We knew from the version 1s and the fact that they sank in wet conditions, and that they caused they had the potential to cause some damage, and we knew we needed to improve that. So one of our requirements had been that we wanted to minimize that as far as possible. So we used that to help us with basically maximum mass of the vehicle, and also the tire selection that we were going to make for the vehicle as well. So we tied that together with our steering models to basically build allow us to build up a really good understanding of our tires and the maximum mass of the vehicle. So another key area, as I mentioned, was the stability of the robot. So as we were moving around in the field, there was lots of twist and flex within the chassis. There was also a very rudimentary suspension design that just didn't really give us particularly good performance. And so what we found was that the imagery was being compromised by the fact there was lots of movement within within the chassis, but also lots of movement within the boom in sort of unfavourable ways. So we enlisted the support of a consultancy called Randall Engineering, and they basically took some ground profiles, so some profiles. We basically went out in the field, took a load of measurements of the conditions within the field. So we kind of looked at the lumps and bumps and features within the field, and we went perpendicular to the crop rows. We went at 45 degrees to the crop rows, and then we went in line with the crop rows, and then we kind of looked at what we called macro and micro features within the field, and we took all that information, and that allowed Randall Engineering to basically look at the frequencies that the robot suspension was going to be exposed to at a set operating speed, which was incredibly useful for us because it basically gave us a model to start to understand the suspension requirements. Alongside that, they also produced what's called an Adams model, which is effectively sort of a more complex simulation with representations of the robot, but with the real understanding being on the loadings of specific nodes of the system. So looking at the suspension. So on this robot, we had a trailing link design. So we had that represented within the Adams model, and it also allowed us to look at the behavior of the boom as well. We have I think it's that robot is just over 5 meter boom with a 6 meter image capture width with the cameras as they were set up. So we had a large boom mounted in a central point, so we needed to know how to understand and manage the movement within the boom. We knew that any small lumps and bumps in the field could potentially cause quite a large movement certainly in the end cameras. And so what we wanted to do was make sure that we mitigated that. So the Adams model was a really big part of helping us with that, and it also helped us then beyond that with our load cases and our FEA studies. So our finite element analysis of individual components gave us the individual loadings on each of the parts, and allowed us to sort of understand whether our design was going to kind of pass or fail from a structural perspective. So that was particularly useful. And then manufacturing. So basically, we worked with a third party up in, they're based just outside Newcastle for the manufacture of these robots. So we commissioned them to build 2 robots to our prototype design. Lots of lessons learned there. I think by both parties, we probably didn't have a mature enough design to deliver to them, to allow them to sort of deliver the hardware in the way that they wanted to work. So I think we ended up with our team on site there quite well the whole time, basically supporting the build of the robots, making sure everything was moving kind of in time, and then we were making sure also that if there was any actual sort of design issues or things that needed to be sorted, we had people there from our team making sure that we were sort of filling the gaps on those. So really useful experience, and we got 2 robots out at the end of it, and I think it certainly helped steer us on our sort of manufacturing approach going forwards. We're now we're much keener to do our prototype manufacturing in-house. So we have full control over the supply chain, full control over any design changes, and that allows us to make sure that the design is much more mature. So and then what we would look to do then to scale, if we wanted to scale, was we could again work with that third party to say we've got a much more mature design, we've got a much more mature drawing pack and understanding of the information of the kind of around that, and then we're in a much better position for them to actually help us to scale and produce at scale. So I'll play a short video. It's just a bit of a time lapse of myself and James putting together some stuff up on site. So we're building up some of the leg units here. So these guys had a really nice, super nice facility doing some really, really impressive stuff. So it was really, really, it was just sort of really cool just to be up there and see how those guys work and kind of what it takes to, you know, produce at scale. So and we did have a lot of support from their team as well. So it was a joint effort, and I think, yeah, we've been using those robots for the last 2-3 years. So they've certainly earned their keep. So I'll go to the next slide. So what do we end up with at the end of it? So this is Tom version 3. So we ended up with 2 of these robots, and some serious improvements as well when we compare that to Tom version 1. So we dropped the mass down from sort of 450, 500 kilos down to sort of just over 230. Ground pressure dropped from probably well over, I think it was well over 100 kilopascals down to 33, which means that critically we can drive on the crop at the earlier growth stages without causing any damage. Our max forward speed was up to 1.5 meters a second, which was critical to getting our coverage rate up to the roughly 20 hectares per day that we were looking for from this robot. I think we had about 3.24 hectares an hour. 6 cameras. We've got a ground clearance well in excess of what we had on the original robot. Still got 4-wheel steering, still got 4-wheel drive as we had before, but crucially, the robot had enough torque to allow it to climb pretty much whatever we pointed at in an agricultural field. We've been on some fairly steep slopes, and as long as we're sensible about the direction we travel, we can climb those. It will climb itself into the back of the van, and we've got much more confidence in the steering system as well, and that's sort of proven out now through a few design iterations. And I'll show you a quick video here of this. Is a nice promotional video we did a couple of years ago for this robot. So as you can see, there is some movement in the boom, the camera boom on this robot, but it's understood and known, and it's within the parameters of the camera. So there's actually a small sort of rubber damping bush in the center of the boom, which allows it to sort of pivot about its center. And then crucially, we make sure that the mass across the boom is balanced. So it's not a jerking sort of motion. It's much smoother, and it allows the cameras to keep up. And crucially, the key thing this robot had to do was gather geolocated imagery, and it allowed us to do that and to do it very well. So that's kind of shown you a little bit about, and I've kind of breezed through it fairly quickly, but shown you a little bit about kind of how the approach we took and the learnings we took from version 1 to version 3. And then I've got a little bit more. So what's next for SRC? So you could have guessed it, I suppose, but Tom version 4. This has followed a similar approach, although we've had to prove out a lot less in the way of kind of fundamentals with this robot. So it's more about refinement. We've got crucial thing that we've done is the modular approach, and I think you can see in the animation there. I'll just try and move it, but how do I get back? There we go. Try and move this out of the way so I can show you. So modular approach, we kind of have the robot effectively is 2 halves, which allows us to sling whatever we want into the center between the 2 halves. So we can have a scanning boom, we can have a spraying implement or tool, we can have a planting tool, we can have we've looked at various other weed control methods such as sort of electro weeding. All of that becomes possible with the same core architecture, which is really, really key for us. It means that we can maximize the value of the platforms that we've built. So we have a number of these robots built up, and it allows us to get the absolute most out of them. When we're delivering what we do, we deliver it as a service. So we we retain ownership over the hardware, and the farmer pays us for the service that the hardware delivers, and ultimately the insights with version 4, it's the insights that come from analysing the imagery, and so that's the value add for the farmer. So we can maximise the value of the hardware by making sure we can use whatever implements you want to put in the middle there. It also allows us, crucially, to change the track width of the robot. So if we want to operate over a particular bed crop or anything like that, we can just adjust to suit customer requirements with a relatively cheap to manufacture fabrication. And that's another key thing that we've kind of moved in the direction for these robots, is that a large amount of their structure is actually a welded, fabricated frame, and that's been a conscious decision to allow us to be quite agile with our approach around the design. If we want to make changes and things like that, we can do that very quickly. We can bolt things on and off of around the box section. We can try things out really quickly. But also the chassis from the version 3 was a bonded monocoque structure, which was super nice from a mass and stiffness perspective. It was super light, really stiff, but it wasn't very flexible. It didn't allow us to make changes easily, and it was, I kind of liken it sort of almost like an F1 car. It's very specific to one application, and what we need is something like this where we can put various hardware in and out. And in this example, we've got this set up as a Tom version 4, so we've got a boom there. We've done some more work on the suspension system, so we've got those suspension units can operate in any direction, so they're much more neutral about their center axis, so we don't have any sort of tuck and duck that we used to get when we had under braking the robot with the version 3 robots with duck, which was because they were training link design, whereas these robots are much more sort of stable and neutral, which means that we get good imagery, but also if we're putting anything near the soil or engaging with anything near the soil, those elements don't get driven into the soil if we have to do a quick stop or anything like that. I think the last couple of things to mention on that one is that this robot can be deployed with a single person, so it fits in the back of a Mercedes van. We drive it out the back of the van, and then one person can fold the boom out, deploy, press a few buttons on the tablet, which is kind of the interface for the user, and then send it on its way. So it's a really I'm really pleased with these robots. I think they're a huge leap forwards. And we've dropped the ground pressure a little bit more again. We've got some much nicer floatier tires, which allows us to actually, if we operate with a slightly higher payload, the tires deflect a bit more, so we don't really see any increase in ground pressure or any damage to crops. So it's been a big leap forwards. And then I've got a video to show you, which is kind of a bit of a little bit from kind of behind the scenes kind of thing of things at Small Robot Company, and also you'll sort of see a little bit more of these robots and them in action. So if I go. So I have finished a little bit early there, but there's plenty of time for questions if anyone has any.
Okay, yeah, I was typing a question myself then, hence the delay.
Yeah,
which I've not pressed go.
right.
Yeah, thanks for that, Ray. That was really interesting. It's interesting to see that next step, that sort of modular approach coming with the version 4. I've not seen that before. Yes, there is a few questions. Mr. Stafford, do you want to make a start? John Stafford?
Yeah, it was just an immediate reaction to your title, treating individual plants, and you showed a stem of wheat. I can certainly see that the role of robotics in high value crops, but individual cereal plants, is there ever going to be an economic case for that?
I think the economic case kind of comes in. It's more around. It's the aggregation of that information still, so we can gather that level of data, and we can analyze that level of data, aggregate that information into a map, which is kind of what I showed to it could be a sort of, we don't have them right now, but like a predicted yield map, or it could be a green area index, or it could be a weed map, or a broadleaf weed map, or a grass weed map. That's some work that we're doing, that we're making some pretty good progress with at the moment. So individual images of a wheat plant or a weed plant are not particularly valuable on their own, but aggregated together, they're incredibly valuable, and especially in situations where we've got high inputs and high outputs. Anything we can do to try and lower those inputs, and that's a key thing that we're trying to do with the sort of targeted spraying, is we don't have, and being quite honest, we don't have a commercially available weeding robot, but what we do have is the ability to access commercially available technologies such as sprayers with individual nozzles. So we're working at a slightly larger resolution for that, meter by a meter squared. But the value can be shown to be there, and especially as the prices of the inputs are going up, that's sort of kind of backing up our case of trying to say, more the higher value inputs, the more we can try and do to help minimize those where possible, the greater the savings for the farmer or the grower. I do see a point around the sort of higher value crops, and they are always on the sort of on the radar as such, and we have had some discussions with growers of some high value crops. I won't say who or when or what, but the nice thing about the hardware side of it is that we're super flexible with the modular approach. So we could say, now we can go down and fit down your row crop, or your bed top crop, or your baby leaf salad, or whatever it might be. We can now go down there and help to offer those insights as well. So I think the case is there for the cereal side of things, but I think our technology's got sort of a broad range of applications as well.
Yeah, no query at all about patch spraying or that sort of thing. Definitely. But it's just the idea of actually changing the treatment of individual cereal plants. I think I don't believe that.
I think the other key thing to know is if you can make a decision to not do something. So that's been the key thing that a lot of our customers and people we've spoken to is, do we want to make the decision? Do we want to say, it's more about having the confidence to not treat that plant than it is to say, I have to treat everything. I'll leave it at that, and we'll move on to another question. But I hope that's tried to sort of
okay,
an insight.
Tim Reynolds.
Yeah, fantastic presentation. Thank you, Ray. I was really interested in how you go about, obviously that boom in the video was deflecting quite significantly. What sort of accuracy are you getting in the Z horizon of that mapping role of the robot, and in particular, yeah, how you, as a relatively small company, how you accessing these sort of quite sophisticated software algorithms, and unless you actually go to a proprietary company like Trimble to actually buy a complete system. Is it quite trivial for a small company? Is it something that actually you've been able to get to grips with, or is it something that actually you're having to buy in that proprietary system?
So I suppose there's sort of a couple of elements there. So we're currently using some open source off the shelf sort of development kits. I'm being very honest about that. So for the GPS. So we're not having to work directly with Trimble or anyone else like that at the moment. We set up a base station in the field at the moment to sort of give us that. My understanding is, and I'm sort of stepping slightly outside of my wheelhouse, but I'm happy to sort of try and explain what I can. But we're able to sort of post process that information and make sure we then get that fixed relative, so we can get it sort of down to a certain level of accuracy on the day, and then once we analyze the information, we can hone that in further, because we've got our base station to help us do that. We're not using any sort of other any sort of third-party providers at the moment, but we're looking at doing that as part of our sort of effort to scale. So we need to start tapping into basically anyone that can give us an RTK fix that doesn't require a base station in the field, because base stations in the field are difficult and timely they take a long time to set up and get things right, and they're also sort of another potential weak link in our chain of getting the robot out into the field. The cost, the cost of the service always gets drawn back to any time a person has to be involved in it. So the whole push is towards the autonomy of the service. I'm not going to stand here and say it's autonomous now, but we're on the path to autonomy. So anywhere where we can lift someone out of the field or having to do a complicated task like setting up a base station, we're looking to do that. But our current solution is an off-the-shelf development kit that allows us to do that. In terms of the accuracy, my understanding is, because the geometry's understood for the boom and the position of the GPS modules on each end, that we have a pretty good understanding of the relative change between them. So we have kind of effectively, the robot has there's a bit of a model which is based on the geometry of the robot as it stands, and I think with the version 4 we've kind of moved away from this swinging boom approach. So I think there may have been some drive from that angle as well, to say, you know, if we've got GPS units moving up and down too much, we're going to start to lose accuracy, and it's going to start to have some sort of complex interactions on accuracy of information within the field. So we've now moved our GPS sensors, and they are kind of core to each sort of side module of the TOM version 4, and lifted those off of the boom. Again, we've still got that model of the geometry of the camera position relative to those, but it's a little bit more fixed, and we get less movement in the field. So, and it kind of comes along, like that side of it kind of comes along from the approach we took with version 1, you know, kind of give it a go, set out some requirements, and then start to refine them, and we're kind of learning all the time with that. So
okay, Mike, you're on mute, Mike.
Unmute me. Thanks, Ray, for the presentation. Very informative. We're obviously aware of the implications on autonomous machinery and safety. So really a two-stage question. You know, how are safety standards applied now, and with industry leading the development of standards, is the small robot company involved in any of the stakeholder groups?
we are indeed, yes. We're involved, in my understanding, in some of the code of practice work that's being undertaken for the use of autonomous farm machinery. A member of my team, Rianne, has been supporting on that, but I don't know all the fine details. But I know that we have had a seat at the table, and we have been helping to try and input into that to try and make sure that, you know, we have our say as someone that's kind of actually doing this. And I think that seems to have been the drive. That actually seems to be the drive to, I've lost my train of thought there a little bit. Yeah, to actually people that are doing things in the field. And it's been a bit like I think there's been a lot of interest around like the hands-free hectare as well from that angle. They've had a go, they've been doing things, they've been operating, and that information now needs to come back and start to help form some of that side of things. So I know we've been inputting to the BSI code of practice. I don't know the number of it exactly, but I know we've been inputting into that.
Thanks very much.
That's right.
Okay, Robert.
Yeah, thank you for the talk. I'm assuming that the planting is intended to be conventional, the harvesting intended to be conventional. But in terms of the Tom is for visualizing. So the question is, how close to commercialization is the product, and what type of plants can it be doing the visualization on? And secondly, Dick seems to be the weeder and Harry the harvester, I'm guessing. Are they a year away? Are they 2 years away?
So in terms of the commercial elements of the commercial aspects of the scouting service, we're doing that right now. So we are out running sort of commercial, I kind of call them commercial trials. So we're out in farmers' fields, gathering data, analyzing that data through the data pipeline, and we're pulling that information together for the farmers to show them what's been in there, kind of what we found in their fields, and we're on the path to allowing them to access that information and access actions from that information. So in terms of the scouting service, we're there. We've been operating the version 3s for quite a long time now, so we've kind of honed that in and that delivery of that service. The Dick robot is, to be honest, in some ways, because we've got this modular approach, it's not that far away at all, because we have the modules we can pull together to pull in whatever technology we wish to use. And we've been doing some work with a company called Rootwave to kind of look at the electro weeding approach. And that's been really good, and that sort of helped us to try and sort of prove out certain elements. But we're probably, I would say, a year away from that, and sort of 2 years away or 3 years away from what I would call the Harry robot. And at the moment, the real key focus for us is just on refining the scouting. And I think, well, for my sort of personal opinion on is it in terms of the insights that we can give and the potential for insights that we can give, I don't think we've really scratched the surface with the scouting and the AI and that approach in terms of moving into crops that aren't broadacre crops, or moving into other types of broadacre crops that aren't wheat or barley, to sort of try and access value through that. So I think that we're certainly on a track to being sort of commercially viable from that perspective. And then, I mean, we're looking at continuing our kind of commercial trialing. I think it's March time next year, kind of roughly. It depends on the growth stages of the crops and kind of how things are moving forwards there. So yeah,
I guess you are dependent on the seasons for the trials, aren't you?
Yeah, we are from a crop perspective. We do a lot. So we're very fortunate in our location where we are, and we didn't used to be quite so fortunate. But basically, we have we're a small industrial unit in Porton, just outside of Salisbury. But from there, across the road is a field which we've rented, which is absolutely, it's just been a complete game changer for us in terms of the speed and pace of our development, because we can take a robot. We've even had to figure out how to take a robot across the road, which it sounds like it would be an absolute nightmare, but actually it was fairly straightforward. So we can take the robot across the road, and then we can go and deploy it in the field. And actually, there's a lot of information we can test and gather that doesn't require a crop in the ground as such. We can just run it across a field of grass. There's a lot we can gather there. We do have some crops in the ground there too. We've been doing some work with IAgrE, and so that's been really, really handy. But yes, you're all right. Ultimately, if we want to start showing the value of what we're doing, we have to we have to do that with crops at the correct time, and with real farmers' fields, which is what we're doing.
Thank you.
Yeah, that sort of leads into my question a bit. Is that original mission of what the small robot company set out to achieve changed? In that, is the plan now to offer a flexible service? Because it sort of strikes me as that scouting service is a service that could be provided on its own to a number of farmers to go and collect data on plant health and then report back, and then that part of the job is finished, and then the farmer takes over and carries on with his conventional spraying and weeding.
Yes, yeah. So I think, yeah, we've kind of, so that some of the commercial approach has been to sort of try, and what we found with a lot of farmers was they're more than happy to sign up to do some trials on a small area, because they want to sort of, they don't want to put their entire farm over to being sort of overrun with robots. What they want to do is understand it and have a use case in their fields, understand their conditions, their crops, what's going on in their fields. So loads of people would say, I'm really keen to sign up, and I'm happy to pay for your service, but I want to limit myself to 20, 40 hectares, relatively small amounts of area relative to their actual farm size. So the approach that we're taking is all about utilization of the hardware. So making sure that we don't have to have one robot per customer if that one customer at the moment only wants to trial in a small area. So we've sort of setting up what's been called kind of pods of farmers. So farmers that are all relatively local to each other that we manage, and so we'll go out with a service team. We own the robot. We employ the service team. They figure out how best to go and sort of serve the needs of those farmers. And then we make sure that we're getting the absolute maximum value out of the robot. So
you end up being more of a service provider rather than a machinery supplier.
Yes,
You basically pay for the service, and you come out with your own equipment, rather than the customers investing in buying the equipment themselves.
Yeah, so exactly. Exactly that, and we're kind of following. We've termed it farming as a service in the past, but I think it's more commonly known as robots as a service, as RAS, as people call it. So that model is being applied in other industries, and I mean, we're not adverse to hardware sales, and we are doing our work towards making sure that we're sort of UKCA approved to be able to go and do that, and we're doing the due diligence and all of that, and with that is in process right now. So we're working on that to allow us to actually sell hardware. So we're not adverse to that, and I think we're kind of seeing. You have to kind of see what the push and pull is from the farmers as well. I mean, one farmer might turn around and say, "Look, I absolutely love it. I just want to run. How much can a robot do? I just want to run this service. I want to run this myself. I want to own the hardware." We wouldn't be adverse to that. We just have to make sure that we're still able to add the most value. But at the moment, the way that makes most sense is to be that robots as a service model and own the hardware. And it's good for us as well, because it means that we can make sure that we can, you know, if we did move into other crops, we can then start to extend the operational sort of time period for that scanning service as well. And then if we move into being able to use other technology on those robots as well, they're sort of, we can be in a position where they're sort of as close to 100% utilized as possible, which is the best for us. We're getting the most value out of the hardware, which is currently quite expensive because it's produced by hand by effectively a team of, well, my team and a couple of the other team of engineers. So yeah.
Okay, thank you. Ken Pollock.
Good afternoon, and I wouldn't wish to sound too negative on this, but I'm reckoning from what we've seen so far, the value of this operation is a function of the value of the cost of the spray, because you're going to minimize the amount of spray used, or alternatively, or in addition, the fact that spraying in the wrong place might do harm. And I just wonder whether that actually is, well, that's just in that particular area, to think of needing to have a robot to do all of this and all the sophistication of it, just to actually minimize the danger of the sprays or the use of the spray seems a little bit unrealistic. And I don't want to sound too Luddite on this, but I mean, you can probably see now I'm a pretty ancient bloke. I did my degree 60 years ago, and we were talking about driverless tractors there following buried cables because there was no such thing as GPS. So in the sense, in those 60 years, we haven't made an awful lot of progress. But do you think that there is a sufficient concern about the danger of the sprays or the cost of the sprays for that to be the first example you're working on?
I think there's a number of areas there. I think some of it is where there is a case, I think, around reducing spray applications from a cost perspective. There's also a case to say that there's been a lot of pressure and is continuing to be, and it's not going to go in reverse, I don't think, in terms of the pressure on spray manufacturers to make sure that they're being super accurate with what they're putting on the fields. And I think at the moment there is a lot of concern with some of the bigger agrochemical firms that they're going to start losing licenses for some of these chemicals if they continue to use them in the way that they use them. So using them in a controlled and understood way, I don't think can ever be a bad thing. I think there is a business case there, and I think there's to only think about it as spraying is to probably slightly undervalue the capabilities and the insights that we can gather and inform. I mean, the exact same data that we're gathering could be used and will be used to inform nitrogen applications. Well, probably, I don't know, 5 years ago, everyone would have gone, oh, well, yeah, but it's not that big a deal. But right now, when everyone's looking and nitrogen's increased and is a higher percentage kind of cost as an input, now everyone's really interested and really keen on that. And there's obviously other data you can gather from satellites, etc. But I think the level of data that we've got here, and that's what I was trying to say, like the value of one image of one wheat plant in one field is zero, but the value of all of those specific images scaled up as a map is kind of inordinate, really. You can start to make loads of different decisions as a farmer. It's more information, and it's being the key is to make sure it's delivered to a farmer in a way that they can interpret it and also understand cost savings. So we're building that into our interface. And when I said that was that 51% saving on that particular example, that's part of the user interface. When you get your information, that pops up and says, if you're using a nozzle controlled sprayer, and you can input that information to say, exactly how that is structured out, what size spray, etc., what's your patch. This is how much we could save you based on this particular input. So, and the really nice thing about that is knowing before you go spraying. So you can have see and spray, and there's lots of systems out there which will do like green on brown, where you can just go, right, okay, here's a weed. Whilst I'm here, I'll spray it. I can see it, I'll spray it. The problem with that is you don't know how much you need to put into your tank of spray, your sprayer tank. So you either have to make a bit of a guess and hope that you get it right, or you end up with a load left, or you end up running out halfway through. So I think the nice thing about that, a nice thing about what we do is, you know exactly how much you need to mix up before you even head out, and you know what that's going to save you in monetary terms. And you can also, if it's a particularly forgiving field, you can even miss out passes if you decide that there's no reason for me to go and do that pass. Well, that's a massive cost saving, because that's someone's time that you've saved, and that's always one of the biggest costs in any system, is someone sat on a seat. And that's why our big push is towards the autonomous side of things, to try and basically, you know, have that robot gather that information, and then you can start to make decisions where you're basically saving people time, and that's probably one of the biggest savings. So